We're going to have the last presentation. It's my pleasure to present Angel. He is the director of ICSO Group, located in Castelldefels. It's belonged to University Oberta of Catalonia. He will explain us biased randomized algorithms and application. It's a very interesting approach to solving the optimizations problems and related to the randomized process.
Thank you, Sarah, for your introduction. I will promise not to talk a lot about the scheduling or to talk more about the scheduling today. So first of all, I would like to say hello to the people, to my students in Riga, because they are watching us at the moment from there. So hello to all of you. So I'm going to introduce this topic, which is biased randomized algorithms, and then some applications of this concept. The topic today, although it will seem similar to yesterday's topic, because of course the applications are quite similar. We apply these ideas to logistics, transportation, scheduling, telecommunication systems, and different finance, different fields. So the application fields are the same as, more or less, the same as yesterday. The topic is completely different in some sense, because today I will not talk at all about simulation. So what I will explain today has nothing to do with simulation. That's what I explained yesterday. So in our group, we have like three main methodologies. First one is biased randomized algorithms. Chronologically speaking, the first one being developed is biased randomized algorithms. I think we started to develop these ideas more or less in 2008. Then we developed the idea of heuristics, that I explained yesterday, the combination of simulation with optimization, with Metaheuristics. That was more or less about 2011, 2012. And recently we have developed another idea that Jessica explained yesterday, which is heuristics, more or less in 2016. Okay, so although chronologically speaking, the first one was biased randomization algorithms. Of course, you can combine these ideas because currently we are using biased randomized algorithms together with heuristics. So we are combining these two concepts, but they are different concepts. They have nothing to do at the first view. Some people mix them or think they are the same because biased randomized algorithms, they also use some kind of random sampling. So they think this random sampling is simulation, but it has nothing to do. Just the key factor here is today I will not mention anything about stochastic problems, not uncertainty. We are just solving optimization problems without considering any uncertainty. Okay? So this is more or less an overview. I will give a brief introduction to analytics and OR as we see it from our group. Then I will explain some basic concept of biased randomized algorithms, and then some examples and applications. So let's go with that. So I guess Elena explained this very well in the first day of the workshop. So we'll not be, it will not go in many detail. But when we talk about analytics and operations research, we can say this. We can see three different types of analytics. Okay, so we have descriptive analytics. So mainly it's about describing the data you have, right? So using data mining or statistical techniques to describe the information, the data you have, or to transform this data into information and knowledge, okay? So this is descriptive analytics, and of course it's strongly related with big data. Fatos did a marvelous presentation before talking about these topics, right? So then you have predictive analytics. Predictive analytics is more related to forecasting the future. Okay, so you use the data from the past to forecast the future. You try to learn about some patterns that can give you hints about how the future will be. Okay? And finally, we have prescriptive analytics. Prescriptive analytics is related to use this information, use this data, use this forecast to take the smarter decisions. Okay? So this is more about optimization and simulation. Okay? Currently in our group, we are more focused in this section. So we use mainly simulation and optimization techniques to try to support decision makers in taking intelligent, smart decisions. Currently, we have a lot of tools, a lot of methodologies, a lot of tools. Also, from a technical point of view, our computers are improving every year. I always say the same. Nowadays, my cellular phone is much better, has much more power than the computer I used to do my PhD dissertation, and it's not so far away in time. Okay, so you will see in 10 years from now, your mobile phone is going to be better than the workstation that it took Javier 9 months to get from our Office of Support to Research. Okay, so this evolution, we have to take benefit from that. We have to consider that this evolution exists, and it goes in our favor, because the technologies that we are using now, the methodologies we're using now, which are computing time expensive, they are going to play an important role in the future. Okay, so there are plenty of methods in OR and computer science and in the interface between them. However, these methods, as Fatos also explained before, they are not fully applied in most companies yet. So we can see a gap between what science has, the methodologies that science can develop, and what companies are using. So then opportunities arise to transfer this knowledge from universities to companies. Okay? We have here today some representatives from Italy, from Actor Company, which is exactly doing that. They are a spin-off from University of Roma, and they transfer knowledge from the university to these companies, okay? Because they know that there is this gap, this need for new methodologies, or the use of these methodologies in real-life applications. So today we have pure methods. We have approximation methods like Metaheuristics, and we can also take benefit from parallel and distributed computing, as Fatos was suggesting before. And there is also a concern for developing smarter and greener solutions. So this is also something that is every time more important, which is consider environmental aspects in your decisions. So not only you don't only care about monetary cost, but also you try to include some additional environmental or environmentally friendly solutions. Okay, this is important. Also, Fatos mentioned that before when he was talking about energies. So what I will explain today is not my work, it's the work of a team. So we are a group of people working on these ideas, and so what I will explain today is a collaborative work developed by the team at ICSO, the group ICSO. Okay. So about bias randomized algorithms. Well, I guess all of you know about the concept of heuristics. Heuristics are nothing more than simple rules, logical rules that you have to follow in order to generate like a pattern or a solution. That's heuristic. Heuristic is a set of steps or a sequence of steps that you can follow in order to reach some solution or to generate some solution. That's an heuristic. So the problem with the heuristic is that they are really fast, because science is a series of steps. A modern computer can run these steps really fast. Even if your problem is NP-hard, large scale, you can run a heuristic in probably milliseconds and get a reasonably good solution for that problem. This is interesting. The problem with heuristics is that they are deterministic. So the series of steps that you are proposed to take, they are always the same. Typically, you have a list of potential movements, so you construct your solution one step at a time, and you always choose let's say, the best movement or the most promising movement on the short run. So you have a list of potential movements, and you always choose the next step based on, okay, which is the one that seems more promising to me? Okay, so you sort the list according to which is the most promising one, and then you choose the most promising one. That way, you are constructing a solution step by step, always using the most promising movement on the short run. Being on the short run, it doesn't guarantee you that on the long run, this movement will be the best or will generate the optimal solution. Okay, this is the problem with heuristics. They are deterministic processes or algorithms. They generate very fast solution in a very fast way. However, you have no guarantee, in fact, it is rarely the case, that they will give you the optimal solution. For that reason, scientists, we like to complicate things, so we develop Metaheuristics. And Metaheuristics are something like, okay, I have a heuristic. What if I introduce some randomness, and I do this, and I do that, and then a local search, and then, so this is Metaheuristics. Okay, so Metaheuristics can be seen like the big brother of heuristics. Okay, you have examples of heuristics like the well-known Clark and Wright savings heuristic, or the NEH, or the PS, etc. So for almost any interesting problem out there, it is almost sure that some researcher, at least, has developed a heuristic that works. Okay? In some cases, these heuristics were developed in the 80s or in the 90s, where computers were really slow. About Metaheuristics, we have been mentioning a lot of examples of Metaheuristics during the last days, like the Boost Search, GRASP, ILS, genetic algorithms, ACO, simulating annealing, and so on. So there are plenty of stuff there to choose from. I also agree that there is no Metaheristic better than any other. It depends on the design, how you design the Metaheristic, and the problem you are facing. So if you are a good designer, you design your Metaheristic in the right way, the differences between using one Metaheristic or another should not be significant. Okay? Nowadays, the world of Metaheuristics is really, really big. Last summer, we organized the Metaheuristics International Conference here in Barcelona, and you can find Metaheuristics almost in any field of application. Okay? And it's really very large research area. So as I said before, the problem with heuristics is that they choose the movement one step at a time. So you kind of sort the next potential movements in your list, and then you prioritize this list based on some criteria or some criterion, and then you choose always the first element in that list to construct your solution one step at a time. This is good, but being deterministic, it doesn't make sense. This is good, and this runs really fast. But being a deterministic approach, it doesn't make sense to run the same process twice. Why? Because if you run the same process twice, you will get exactly the same solution. Okay? So you gain nothing by running this deterministic approach several times. This is a pity. So somebody can think, well, what if we introduce randomness into this deterministic process? So if I introduce randomness into this deterministic process, I can run the process multiple times and then generate different solutions and then pick up the best one from all the solutions I can generate. Yes, that's true. However, computer scientists, how many computer scientists are in here? Computer scientists, they do not know that there are other things apart from uniform randomization. So when computer scientists try to do that, they use uniform randomization. If you use uniform randomization, then you have a problem, because you are destroying the logic behind the heuristics. So if you introduce uniform randomization into the process to transform a deterministic process into a stochastic one, into a randomized one, then you are destroying the logic criterion, which allows you to sort the list of potential movements. Okay? And you can check that if you take one good heuristic, which follows a logic process, and you introduce uniform randomization in there, in that process, you can run that new algorithm 1 million times for 1 million years, and you will never beat the solution of the heuristic, which runs in milliseconds. Because uniform randomization, it just do things without any sense. Okay? So on the one hand, that's good because you can run the heuristic multiple times and you will generate different solutions. But on the other hand, none of these solutions you are generating is going to be good. Okay? None of them. So is there any other approach that you can use to generate multiple solutions, but without destroying the logic behind the heuristic? Is there any other way? Yes, there is. Don't use uniform randomization. Use some biased randomization. Use something, not a uniform distribution, to introduce randomness, but what if you use a skewed or biased probability distribution to introduce this randomness into the heuristic? Then what I am suggesting is more or less similar to what Christian was explaining yesterday for uncolonial optimization. What if you introduce some ways, or you assign more probabilities to those paths that are giving you better solutions, that are more promising? So put in different words, instead of always choosing the most promising solution at each step, or instead of using the next step uniformly randomly, just assign some probabilities to each of these potential movements. The more promising the movement, the higher the probability you should assign to it. Okay? You can do this as ACO and colonial optimization do, but by using empirical probability distributions. That's good. So you use some parameters, you define an empirical probability distribution, that's perfectly fine, and more or less that is how ACO works. However, in our experiments, we noticed that empirical distributions, they introduce more parameters, and on the other hand, they are computationally costly, expensive. Okay? So we came out with the idea of using theoretical probability distributions instead. So skewed distributions, non-uniform distributions, but theoretical. Why theoretical? Because a lot of people have studied these distributions, and you have analytical equations, analytical formulas that can allow you to generate very quickly random numbers or random variates coming from those distributions. So from a pure efficient computational point of view, this is much faster than using empirical distributions, okay, which is good. So this is more or less what we are doing in biased randomized algorithms. We are randomizing the logic behind the heuristic by using non-empirical, non-uniform, but theoretical skewed probability distributions. Okay? So this allows us to run multiple times the heuristic, and every time we run the heuristic, we are likely to get a different solution, but a good one, because it's mostly this solution is respecting the logic behind the heuristic. Okay? And odds are that when you run this randomized heuristic several times, you will find solutions which significantly improve the one provided by the heuristic. And we are talking here about milliseconds. And we are talking here about something that can be run in parallel in different cores, in different computers, or in a GPU. These ideas are more or less explained in these papers, or these are examples. This paper is, I think, is the best one explaining these ideas, which is quite recent, 2017. Alex did a good job, I think, together with Elena and Javier, on explaining these ideas. Okay? And then there is a previous paper also with Elena and Javier, which we call Mirha, which is more an application case. But this is a very good paper if you want to understand or to read these ideas in detail. Yeah, so basically, as I was saying, we, instead of using a uniform distribution, we use a skewed probability distribution. So some of you might remember or might recall that, oh, okay, these ideas are similar to GRASP to some extent. It can be seen as a particular case of GRASP. GRASP, what GRASP, the basic version of GRASP does is, okay, you have the list of candidates for constructing the solution, and then you decide to assign the same probability to all the candidates in the list. First, you can cut the list at some point. So you restrict the candidate list. You restrict the size of the list, and then you assign a probability, a uniform probability to all the elements in that list. So to some extent, the idea what we are suggesting is something like a biased GRASP. Okay, so we are saying, no, we don't want to cut the list. We want to consider all the elements in the list. Because deciding where to cut the list is a difficult decision. You may be getting rid of good solutions or good movements. Okay, so we prefer to keep all the list, all the elements in the list, but assign them different probabilities. For two reasons. Okay, so we reduce one parameter in our decision, but even more importantly, it doesn't make sense really. If you cut the list and you assign the same probability to the first element, to the second one, to the third one, to the fourth one, and so on, it doesn't make sense to us. Okay, it makes more sense that you assign more probabilities to the elements at the top of the list, which are the more promising ones. So the more promising an element is, the more probability he will have of being a chosen. Okay? So yeah, this is what we are doing. So basically what we have, I think this figure illustrates this quite well, is this is a heuristic. A heuristic will generate one list, and then it will provide one solution. One list, one solution. Good thing is really fast, milliseconds, milliseconds, even for very large problems. NP-hard problems, very large scale, milliseconds. Okay? Now what we're saying is, okay, what if we introduce some bias randomization, some skew probability, and then we mix this list a little bit, okay? We mix this list a little bit. We can generate like different combinations of this list. All of these combinations are strongly correlated with the original one. The order in this list is strongly correlated with the order in this original list. However, they have slightly different positions to some extent, okay? For each of these new lists, you are able to generate a new different solution, okay? And all of these new solutions, they are going to make sense because basically all of them are still relying on the logic behind the heuristic. Okay, we'll see some examples later. Now this is a little bit more fundamental, but we will see some examples later. Good thing about this is really, really fast, really fast. Notice, this takes milliseconds in a computer. How long will it take to generate these different solutions? Let's say this is 1,000 solutions. How long will it take? Exactly the same time than this, because you can parallelize this. You can run each of these lists in a different thread or in a different core or whatever, okay? So you are getting very good solution in milliseconds, in real time, which for some applications is really important. Imagine, for instance, in telecommunication systems, you need decisions in real time. So these are some experiments that we developed to test this randomness, or how this bias randomization will improve the original solution of the heuristic in almost real time, okay? So without parallelization, but just giving it a few seconds, like 2 or 3 seconds, to see what happens. And you can see that in all cases, these are vehicle routing problems, these are R routing problems, and these are flow shop scheduling problems, okay? So in all cases, you were able to significantly improve the solution of the heuristic in just a few seconds, okay? Just by doing this bias randomization approach. We also did some tests, more intensive tests. They were published in European Journal of Operational Research. They're a little bit for these guys who like Javi likes, this kind of parallel computing or distributed agents collaborating among them. So we generate a platform for parallel computing in which each agent shared information with other agents, and each agent was basically running a bias randomized version of a heuristic. And we did that for the different problems I mentioned before, for flow shop scheduling, for vehicle routing, and for a routing problem. And in all cases, this agent collaboration allowed, just by using a simple bias randomization approach, allowed to match the best known solutions in each of the problems in the literature. Okay? So it's really interesting how parallelization can help you to get good solutions, even when simple heuristics or simple randomized versions of heuristics. Good. So now some examples of applications I can give you. The first one, of course, vehicle routing problem. So this is how we started, really. So we started working with the vehicle routing problem, and we learned a lot while solving the problem. Because the nice thing about the vehicle routing problem is not that you are solving more or less a realistic problem. It's the difficulty it contains and what you learn about optimization, because a lot of problems can be assimilated to a vehicle routing problem, even when they seem completely different. Okay, so as you know, a vehicle routing problem basically consists in delivering some customers from a central depot. Okay, so you have to do that in the best possible way. And as you know, when the size of the problem exceeds the number 50 customers, then probably exact methods are not going to be able to find the optimal solution. So you're going to need Metaheuristics. Okay. I even have participated in some papers, conference papers, in which the co-author was very happy because he was able to use custom programming to solve a vehicle routing problem. But when I was asking him, but how, which is the size of the vehicle routing problem you are solving? So he was answering, okay, we are able to solve problems with up to 11, 12 customers. Okay, so really, using such a powerful tool like custom programming to solve problems up to 14 customers, it doesn't make sense. Okay, so in this case, we also introduced some novelties because yes, vehicle routing problems is just about finding the optimal routes and blah blah blah. But okay, in real life, you may find something that is not as easy to formulate in a mathematical model. Like for instance, you can see here that this might be the optimal solution, and it is the optimal solution for one of these instances, classical instances. But you can see here that you have intersecting routes that intersect themselves. So maybe the decision maker doesn't buy it because she doesn't like their drivers to intersect to each other. Because some customers might see the car passing by and this car is passing by, it's not delivering me. It's delivering other guy, and it's just passing by my retail center, okay? So this is sometimes it's not very polite. Same way here, you can see here, this is an optimal solution from a mathematical point of view, but probably decision makers will not like it. Why? Because how do you explain your drivers that one driver has to do all this route which is very long, while other driver has only to cover, a very short distance. So in terms of work balancing, this doesn't make sense. Okay, so the routes are unbalanced. So even when these are mathematically optimal solutions, real life sometimes gives you some surprises, and decision makers don't like them. Okay, so for that reason, we wanted also to generate a set of alternative solutions to offer to the decision maker. So similar solutions, similar quality solutions, and then you choose. Okay? So I'm going to give an example of how the first time we implemented these biased randomized concepts into an actual heuristic. So the heuristic I'm choosing for that is the well-known and old Clark and Wright savings heuristic. It's quite old. It's from the 60s. But really the guys who developed this heuristic were smart, because the heuristic has a lot of, interesting properties. So what they propose is, okay, if I have to solve the vehicle routing problem, what if I compute something like, what if I first generate like a dummy solution? A dummy solution is nothing more than I send one vehicle to each node, and then to each customer, and then I come back to the base. So basically, I need one vehicle for each customer. I assign one vehicle to each customer, and then this vehicle returns home. This is the dummy solution. And then I compute the savings I get by merging routes. So if I merge this route and this route, I get some savings in my costs. Okay, so this is good. I compute all these savings. This is very fast to compute the computer. Okay, even for large instances. Good. Then what I could do is I create a list of savings. So I sort all these potential merges from the most savings that gives me to the less savings. Okay, so I create this list, and then I proceed to traverse the list making the merges that give me the most savings, as far as they can be done. That is, as far as I am not violating any additional constraint. Okay, so this is basically the current rate savings algorithm. It's a very smart algorithm for its time, and it really works really fast and gives very good solutions. I was surprised yesterday because Christian says something like, for very large scale instances, greedy behavior like this one, this is a greedy behavior, perform very well. The larger the scale, the better they perform. This is something very interesting, that he has the feeling it occurs. And to some extent, I also has the feeling that occurs. And that could be explored in more time if one of our PhD students has the interest to explore this theory. Okay? But if this is true, then this kind of greedy behavior is very interesting. And in particular, bias randomization of greedy behavior is very interesting. So this is the Clark and Wright, basically the Clark and Wright saving. So what we did, the Clark and Wright saving is very fast, extremely fast. I have run some tests in Java, which is not, it's not the faster programming language. But even with Java, you can solve instances up to 500 nodes, the so-called Kelly instances, in 8 milliseconds. So it's really, really fast. So what we did here is, as I was explaining, we introduced this probabilistic behavior into this heuristic I just mentioned. So we randomized it using a skew probability distribution, this heuristic. How did we randomize that? Which distribution we use? Okay, so we use a geometric distribution. Geometric distribution, because it has a lot of advantages. The geometric distribution, we didn't use an empirical distribution because, as I explained before, we wanted to use a theoretical distribution that you could use an analytical formula to generate values from that distribution. It's very fast. Computationally speaking, it gives you a lot of speed. Okay? If you don't fall in that, then okay, you will get the same results, but with much more computing time. Okay? So in computing times, you need to be also efficient. So we use a geometric distribution for different reasons. Once, because it's really simple to generate values from this distribution. There is an analytical expression that some mathematician developed. I believe that. So I can use that expression to generate fastly numbers from this distribution. And it only has one parameter. It only has one parameter that goes between 0 and 1. So that's great, because it only has one parameter, so I can easily do the fine-tuning of this parameter. In fact, we do this fine-tuning every day without spending more of time. Right, Javi? So you only have one parameter, and this parameter goes between 0 and 1. So it's not like the parameter goes between 0 and plus infinite. Oh, that's a problem. Here it only goes between 0 and 1. So it's easy to do the fine-tuning. So, and the nice thing is that if you choose a parameter close to 0, then what you are doing basically is uniform randomization. So on the one extreme, your parameter value is close to 0, you are doing uniform randomization. If the parameter is close to 1, you are basically doing greedy behavior. So you basically are in the heuristic. Anything in between is something in between. So not greedy, not uniform. So you can use different degrees of this parameter to define different shapes for this randomization. Very easy. Computationally very efficient. It works really fine. How we got the idea of using the geometry? Why the geometry? How it came to our mind? So it came to our mind because there are something like in forecasting, in simple exponential smoothing, it's a forecasting method. They use something similar for doing forecasting, for doing smoothness of the time series analysis. Okay, so this is where the idea comes from. And this is very well explained in this paper. Also, one of the first papers we developed in this area of bias randomized algorithms that was published in Applications of Computing with our friend Santi Caballé, by the way. This comes, in fact, from a conference that was organized by FATOS, the HIS 2008. Yeah. So after that, we did some improvements on the algorithm, and we introduced some improvements in terms of local search. So we came to the idea of using a hash map. For those of you who are not computer scientists, a hash map is just like a cache, memory cache, something that gives you memory to your algorithm in a very fast way. And also some splitting techniques. That the idea was a little bit related to, I can solve subproblems of the original problem, and then by solving the subproblem, if I am able to improve the solution for a subproblem, then I will be able to improve the solution for the entire problem. It's not exactly the divide and conquer method, but it has some relationships with that. Yeah, so we did a lot of experiments with a lot of different, you can see here different types. These are all instances in the literature, so they really put instances, like very different instances, very heterogeneous ones, some of them with the depot in the center, at the center, some of them with the depot at the one corner, some of them on the depot or clustered or scattered design. So you have really to have a good heuristic to be good in all these different structures, right? And yes, we proved that our tool or our algorithm was able to improve at the moment the best known solutions and also the computational times. So from here we moved to another example of application, which was the R routing problem. It's the natural way to go. If you are able to solve the vehicle routing problem, then you move to the R routing problem, which is a similar problem, but with some differences. I explained it a little bit yesterday about this problem too. Basically, the differences is now you don't have a complete graph. You have some edges, but the other edges are not available. And you can traverse these edges as many times as you wish. And your demand is not at the vertex, but it is on the edges itself. Some applications of this problem are related to bus services, like picking up students to go to school, or to snow removal. I think I talked a little bit about that yesterday. Or here you have more applications, or even waste collection management. So there's a lot of literature on these problems and their applications to logistics in cities and everything. It happened something that it was strange, because at this time, we were working for, as I explained yesterday, for Sabadell City, developing a project for smarter waste collection, like in waste collection management in smart cities. So we did an interview for La Vanguardia, and then we explained the algorithms, the algorithms, the bias randomization, blah, 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 very interesting. And then the guy who published the article in La Vanguardia, he published something like, the researchers of the ICSO group at the Open University of Catalonia are going to install, the sensors in the containers. Okay, so it was not like that. Okay, so this is the man in the middle problem. You explain something to somebody who is not really in the area, and they don't care. They only want to put a nice something there in the title. Nevertheless, for the R routing problem we thought about, okay, what if we were able to develop a first heuristic that doesn't exist? Because there are some heuristics for the R routing problem, but path scanning or other heuristics. But none of them similar to the savings heuristic we explained before for the vehicle routing problem. What if we are able to develop a savings-based heuristic similar to the one we explained for the vehicle routing problem? So we did that. We tried to adapt the savings heuristic or the concepts of that heuristic to the R routing problem, which is different. It's not trivial. The adaptation is not trivial. In fact, I remember at this time a guy who was working with me, Kim Castellà. He was really smart guy. And nowadays, I try to convince him to do a PhD here in Barcelona, but he said that his girlfriend was willing to move away, so he went away. And I know that because I saw him last year in New York when I was in Jessica in the Winter Simulation Conference. I saw her there because now he's director of I don't know what in Facebook in New York. Okay, so. But this guy, he developed the basic ideas for this heuristic. So he adapted the savings heuristic to the to the routing problem and developed what we call the SHARP heuristic. SHARP. I don't recall what acronym means, but it was something like SHARP. Okay? So of course, we did the same. Once we had the SHARP heuristic, we randomized it. We used a geometric distribution to randomize this SHARP. And again, the results were spectacular in terms of we were able to beat the best known solutions in the literature with a relatively simple algorithm. Okay? And also very fast convergency times. Everything was very nice. Okay? You can see here, this was the old heuristic in the literature, the old heuristic, and this is the SHARP. So you can see in terms of improvement. And this is the randomization, the bias randomization of the old heuristics, and this is the bias randomization of the SHARP. So the improvements were really interesting. So another example, and now I have to go to scheduling. Leandro and Sarah, scheduling. So another example is Flowshop, okay? So we did the same in Flowshop. In Flowshop, it really was a very difficult thing to do because you know that you have there the popular IG algorithm. Sarah knows that very well. And the IG algorithm was developed by Ruben Ruiz and Thomas Asle, and it's really very efficient algorithm for the Flowshop problem. So it was impossible to beat that algorithm. But we got really close. So the idea basically was, okay, we cannot beat this algorithm because it really performs perfectly, but can we do the same without any parameters? So the challenge here was, can we do the same with a parameter-free algorithm? Can we reach the same results without worrying about, I had to do fine-tuning here and there? Nothing, I don't care about fine-tuning. So I want to reach the same results without any parameters. Good, so basically this is based on the NaH heuristic. The NaH heuristic is a heuristic for the Flowshop problem. Sorry, I didn't explain that. The Flowshop problem basically is you assign jobs to machines. So this is job 1 working in machine 1. When this job finishes in machine 1, you start job 1 in machine 2, and so on and so forth. Job 2, who starts in machine 1, then in machine 2, and so on and so forth. So you have jobs and machines, and you assign jobs to machines in a given order. The number of combinations here, if you have n jobs, is n factorial, which is a lot. It's a lot. As n grows, n factorial really grows a lot. So it's a complex problem. And then your goal here usually is to minimize the megaspan. The megaspan is the time you need since you start the job, the first job, until you end the last job. Okay, this is, of course, a simple toy example, but you can imagine this with a lot of jobs, and then the problem becomes really interesting. So there is one heuristic which is called the NaH. The NaH heuristic is basically, I think it was from 1984, something like that. Maybe Sarah knows, more or less. So the heuristic is also a very intelligent heuristic. All these heuristics, you learn a lot from them because they have a lot of logic, of course. So basically, what they do is they short each job. So they take this each job, and they consider what if this job is the only job in the process. How much time will this job require to complete the entire processing? Okay? So this gives you like the total time each job will require. So you can sort now in a list the jobs from most time to less time to be processed. And then what they do is they start picking up the first job, they put it here, then the second job, they put it here, and they try if it would be better to put the second job here or here is good. And then the third job, they put it here, here, here. They try the different options, and they keep the best way. This is a very fast process in the computer. Okay, but it makes a lot of sense, and it works very well. This is the NaH heuristic. So then, as I was saying, Ruben and Thomas, they developed the IG algorithm with the idea, or basically, in my view, it's an ILS with some fine-tuning or whatever, but it's almost the same structure as an ILS. So it performs really, really fast, and for this problem is unbeatable. A lot of people have tried to beat this with much more complex algorithms. Some Chinese guys with genetic algorithms with 35 parameters, and they don't perform so well, so it doesn't make sense. So we wanted to do the same as I said, but without using any parameter, parameter free. Okay, so for this we we took the NaH and we said, what if we introduce Bayes randomization in this process, in this NaH process? And we introduced Bayes randomization, but the problem, remember, the geometric distribution, that is our lovely distribution, the geometric distribution has one parameter. We didn't want parameters at all, not even one. So we think about, and we decide to go with the descendant triangular distribution, something like this. Because a descendant triangular distribution, it has no parameter. You just have your list. Your list defines the starting point and the ending point. That's all. So you use the descendant triangular distribution with no parameters. And we try, okay? We randomize with the descendant triangular distribution. And then we more or less define an ILS structure from Elena. In fact, Elena is a co-author of this paper. We define an ILS structure, and we change the swap, the local search processes. Let's say we did some changes in the local search processes, again, because we didn't want any parameter. And we changed also the simulating annealing, but what we call a credit-based, I don't remember the name, it was something like demon-based approach, which doesn't require any parameter either. So the challenge was, can we do the same without any parameters? Because, of course, in all this process, we were discussing with Ruben also about this has no parameters, yours has parameters, all this stuff between math scientists will have nothing to do in their free time. Okay. So at the end, we got an algorithm, which is this one, the ILS ESP, which was able to perform at the same level, exactly the same level as IG, which is great, without parameters. But we even go one step farther than that, because we show in that paper that but Bayes randomization, by employing Bayes randomization also during the generation of the initial solution, what you are doing is starting from different points. All of them of similar quality, but they are different points, different starting points. So if you introduce parallelization in IG, and if you introduce parallelization in ILS ESP, it results that ILS ESP performs better when run in a parallel way. Okay? So at least in that sense, we were able to improve the IG behavior when parallelizing the algorithm, thanks to Bayes randomization, because it allowed you to start from different points of initial points. Okay? All of them promising. So other examples of applications that we have developed in the past is this. I think this is interesting because it is related to energy consumption, going green, and all this stuff. So basically, this is a research line that also Lorena is now working on that a lot, which is related to what if we use electric vehicles in our fleet. So electric vehicles are nice. You can do a lot of things with those electric vehicles because they improve your pollution, right? However, nothing is perfect. So electric vehicles have several challenges to be solved yet. One of the challenges they represent, they arise, is the fact that they use electric batteries. You can imagine, we are always with our cellular looking for a plug to connect our cellular, right? We spend most of our day looking for a plug to a switch to connect our cellular, to plug our cellular. What happens with the van, with the car, with the truck? You can imagine. You need really a lot of energy because batteries today are not ready for, let's say, long distances without recharging. Okay? And the problem with that is that recharging batteries is not so easy as just traditional fueling. You know, you stop at the gas station, in 3 minutes you have your car full with gas. In the case of batteries, this takes hours. Okay, in electric vehicles, it takes hours to recharge. So the problem with electric vehicles is that this imposes a new condition, a new constraint on the problems you are solving. The constraint is you have a limited driving range. So your driving range is limited. You cannot exceed this driving range. Okay, so you have to solve the problem, but with strict driving range constraints. Okay, this is a work we developed together with some colleague at MIT, who was the one who proposed the problem. It was a challenging problem at the time, because the idea is that you had to combine hybrid heterogeneous fleets of vehicles. So some vehicles with traditional gas, some vehicles with batteries, and inside batteries, you had different types of batteries, like larger vehicles, smaller vehicles, and so on and so forth. But eventually, I think we did a nice, interesting job here, and we were able to solve that problem also in a rational way, showing that the introduction of electric vehicles should not increase significantly the cost of the delivery. Okay? So other applications we have started to scratch, like this one with one of my PhD students, Guillem Cabrera. It was about green internet computing, very strongly related to what Fatos has explained before. But of course, we just scratched the surface, while he has been working on that for a long time, and he's an expert in this area. So I will skip that very quickly. So another application is trade in finance, trade credit, risk analysis. This is a very important problem for companies, because the trade credit is something like, okay, when your customers buy something from you, to some extent you are, if they don't pay you at the time, they pay you like 3 months from now, 6 months from now. This is like a credit you are giving to these customers. So you allow them to pay you in 3 months, in 8 months, and so on. So this is, you are in fact giving credit to these customers. This is called trade credit. And this is a really big problem for companies, especially small companies, small and medium companies, because you can sell a lot of products, but you can get rid of cash flow easily. Because if they don't pay you in 6 months, or, so you're going to have problems, cash flow problems. And your company will have to close, even when it is successful producing and selling products outside. Okay, so here our goal was basically optimizing like a personalized vision or a personalized view of trade credit. So answering questions such as, how much credit can I give to each of my customers, and for how long? Something related to the portfolio optimization problem at the end. But how much credit can I give to each customer, and for how long? Okay? Another related problem, of course, we have solved several rich portfolio optimization problems. Portfolio optimization problems are, you can solve them very easily with exact methods, no problem. But the problem arises when you consider realistic constraints. When you add realistic constraints, then the problem becomes NP-hard, blah, 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 blah. You cannot solve them anymore with exact methods. You have to go with Metaheuristics. Okay, in this case, we solve also the problem with an ALS. It's not an easy problem to solve, I have to say, because there are some details that make the problem really complex, even to generate an initial solution. Another interesting examples of applications we have developed in 2L BRP, most of them in transportation and logistics, because it's where we got our projects in the past. We don't know in the future, but in the past at least, we got our projects in the transportation and logistics area, so we go there. So one interesting problem is this 2L BRP, because it is an integrated problem in which you have to optimize the routing, but at the same time also the packing of the trucks. And it's really complex, really, because the packing affects the routing, and of course, the other way around is true too. So it has a lot of variance. I think this problem was initially suggested by this Italian, this Emanuele Iori. I think he was the first guy working in this problem. Okay, this is based in a real life company case. In fact, the guy who did his PhD on this is a manager in a company in Canary Islands, and he called me one day on the phone, and I didn't know him, and he told me, I want to solve this problem because my company, we rent machinery to building constructors. So we want to solve the 2L BRP because we have to pack the machinery in our trucks and then to deliver these trucks to the customers. And at that time, I had no idea about what he was talking about, really, because it was a recent problem in the literature. But I said, yeah, I think it's interesting. I had no many PhD students at that time, so I thought that it was interesting. So we start to work on that, and then we find these works from Manuel Illori, blah, 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 and we found that it was a very interesting problem to deal with, and yeah, I think we learned a lot with this problem. Other applications in logistics and transportation, probably I would like to highlight very quickly this paper with Jessica, which was about real-life crew rostering problems in airlines with work balancing goals. So it was an easy algorithm, right, Jessica? A very simple algorithm we used there, but it allowed the companies to solve a complex crew rostering problem. You know, in airlines, how the crew rostering of the crew, or the rostering of the crew, but we were looking for balanced plans. So no crew was working more hours than other. So the workload was balanced across the month, across the crew, and across the year. Okay, so thanks to this paper, I think we received a prize in Madrid from the Spanish Minister of Fomento. So Jessica and I went there, you know, very happy to receive the prize. And we had the opportunity to talk to the minister. So another one was, another interesting one is this one, a successive approximation methods for the heterogeneous vehicle routing problem. Heterogeneous vehicle routing problem always complicates things. When things are heterogeneous, bad thing, right? Because you have diversity complicates things in optimization problems. So in this, basically we generate here like a successive approach in which we were solving the problem layer by layer. Okay, so basically what we were doing here, we proposed here a methodology that in my view was interesting because it reduced solving a heterogeneous problem to solving a series of homogeneous problems, which we know how to do that very well. Okay, and the last one is this one with Dani Guimarães about the multi-depot vehicle routing problem, because I think we also learned a lot about this, especially this mechanism of round robin with balancing the depots or the load to assign it to each depot. This round robin mechanism that some of you have been working with, Alejandro, Jessica too, I think. So this mechanism, it seems easy now, but it took us like 1 year to think about those ideas and to develop them. And recent publications now that we have got, I would like to highlight this one, which is a work from Lorena, Sustainable Urban Freight. So the idea here is that we are now trying to consider not only economical costs in terms of logistics activities, transportation activities, but also other dimensions like the social dimension, like the environmental dimension, and so on. So we try to enrich the perspective of the cost with a multidimensional approach, but including this kind of radar graphs that I think they are very useful. Of course, in most of our papers, we use box plots or some kind of analysis graph. And just before finishing, among the current work on bias randomization algorithms that we have now under review in different journals, I would like to highlight this one. All of them are interesting, even the scheduling ones, or especially the scheduling ones with Sarah and Leandro and Daniele. But I think, in particular, I would like to highlight that one because it took us, and Alejandro knows and Javi knows, it took us like forever to submit that paper. Because we were working with Martin Saudesberg, and he's really very demanding. So it's like, I think the paper is ready to submit. No, it needs improvement, it needs improvement. And we repeat the computations like 1,000 times, okay? And well, eventually he was not happy yet, but he allowed us to submit the paper, which was the goal. Because if you don't submit the paper, it's not where that paper is accepted. So the paper is interesting because it solves, or it deals with an interesting problem in my view, which is, okay, it's a multi-period vehicle routing problem, so multiple periods, but you can decide, or you can decide to offer your customers a price discount in exchange of flexibility in the delivery day. So my customers, if you accept to give me some flexibility in the day I deliver you the product, I give you a discount. Okay, with that flexibility, I can save money in the distribution costs. And part of this saving, I can transfer it to my customers in terms of price discounts. Okay, so the idea is, I think the idea is very interesting. And in fact, it comes from Martin because I guess he has this problem there with Coca-Cola and all these companies that are distributing in Atlanta. So to finish my presentation, just to explain that we use bias randomization algorithms basically to improve the behavior of the heuristic, but not only for that, because in fact we use bias randomization everywhere in a meta-heuristic which contains a constructive step. So we use it for generating the initial solution, but also in the perturbation stage whenever there is a destruction and reconstruction process. We observe, according to our experiments, the destruction process can be done at random, uniformly random. So you destroy at random, that's okay. But the reconstruction process, it is much better to do it following some logic, okay? That's where we introduce also the bias randomization, and it, according to all our experiments, it not only improves the heuristics, but when you combine bias randomization with multi-star, GRASP, ILS, BNS, so on, the meta-heuristic is improved too. It goes faster. I mean, it converges faster to the optimal value, okay? And as you can see, the number of potential applications is almost unlimited. You can apply this idea, these meta-heuristics, to almost any field, okay? So just to finish, again, for those of you who missed the presentation yesterday, remember you that we have currently an open call for postdoctoral positions at the Open University of Catalonia, so if any of you is in that situation, we will be happy to consider that application. Also, together with UPF, UPC, and other universities, UP UBNA, and other universities, we coordinate an Erasmus consortium on smart transportation and logistics, including smart cities and a lot of things. So you're a student looking for an Erasmus, you can apply to these grants because we, the professors, are the ones who manage these grants directly. So no university, or yeah, you have to go through university, but it's much easier, okay? And finally, we have this Winter Simulation Conference this year in Göteborg. So I encourage you, it's the second time it comes to Europe. I encourage you to attend the conference if you like simulation because it's really the best simulation conference in the world. This year is in Europe. Okay, I am organizing the track in simulation optimization. So if any of you is interested, just let me know. So thank you very much.
Your interesting presentation with a nice application. Any question? ICSO group?
Yeah, thank you, Angel. Very interesting. I'm just wondering, in some local search algorithms, for example, you don't work with solutions. You work with a list of features of solutions. For example, in taboo search, you don't keep the whole list of solutions because it's not efficient, basically, right? So if you would apply your biased approach to features of solutions, would you expect to get something the same as you would work with the solutions?
To be honest, yeah. I think even in taboo search, you have a constructive process too. So you can introduce constructive process in taboo search, or even in genetic algorithms. There are some you can use mimetic algorithms that include some part of constructive process or some destruction reconstruction process. So at least in all this process, I can guarantee no, but I think my guess is that it could help. For the characteristics, I'm not sure. Never tried.
Okay. I'm going to thank you very much, Angel. You're starting the closing section.
Okay, so this is the last talk. Thank you so much, all the speakers, to come here. I think they are a great talk. I think I'm very happy because I will never expect to have so many people in this room, more the ones who are following us in streaming. So I think I'm quite happy with the success of this talk, and I think we have an opportunity to organize something like this in 1 year, couple of months, and have new speakers, because Celso has to come here, okay? So he just told me this morning that he's doing much better, but I told him now that he's better, that he owes me a visit to Barcelona. I would like to thank the Barcelona Graduate School of Mathematics. So these are the ones who support this graduate course. This is a group of the groups of mathematics in Barcelona. I'd like to thank them for all the support. I would like to also to thank my group. All my group that helped me, Jessica, Alberto, Georgina, Georgina is my support, and without her I could not do all kinds of things. I also like to thank all the speakers, Fatos, Angel, Jessica, Belen, and Christian for volunteer to come here and extend this knowledge to the PhD students, postdocs, etc. As you can see, Metaheuristics is applied to many, many areas, from cloud computing to logistics. So it's a methodology that is applied to many, many areas. It's probably not as known as other methodologies like machine learning that's becoming quite famous. So I think we have to do some marketing here. But I think we are on the 3rd level of analytics. So remember these 3 levels of analytics that I explained the first day. And it was kind of interesting that Sufyan, which I also thank IBM to come here, I forgot about them, Sufyan and to come here. And Sufyan also explained about these 3 steps of analytics. Angel explained about these 3 steps of analytics. So the prescriptive analytics is still not known. But companies will come there. So we should be ready when the company, where there is the boom, we should be ready to answer the demands of the company, because they're still on the predictive. They're still very worried about the predictive. When they solve the predictive, they will go to the prescriptive, because that's where the juice is. It's being able to really automatize the decisions, be automatic decisions. So I think it's interesting. I think for PhD students, maybe you have new ideas how to drive your research. And to finish, if you want to follow all the pictures you can see on Twitter. You can see the Twitter on the UPF Analytics, also on BSCS Math. You have all the pictures there. Okay, Fatos, Angel. I think I forgot one picture only. The dinner, which is always the most amazing part of the conference, right? Jessica, so you can follow the Twitter, and we also will announce the new events on both of these web pages. So thank you so much, all of you. Looking forward to see you in the near future again, and we have bigger room. Okay, thank you so much.